In this session, we will delve into an introduction to Databricks. I have here sample 65, which you can access by clicking on Node Sample Metadata. This will allow you to obtain sample 65, a representation of a Databricks persistent staging solution. To start, you'll establish your connections. As demonstrated, I have a folder containing all my data sources. This includes SQL Server data, flat files, REST API, and FTP or SFTP systems. You might also encounter Parquet files. These are the various data sources we've incorporated into this solution. For Databricks, you'll need to set up a landing connection and potentially a persistent landing connection. This ensures the data you import is stored in a data lake and then in a persistent data lake, preserving the original files. From there, you can transition the data to your staging environment. We've established an ODBC connection for this purpose, which is a placeholder for the integration stage and can be used to import metadata from Databricks. We'll discuss this in more detail later in a future session. Additionally, a compute connection allows for multiple compute clusters if required. For this demonstration, we've configured it for Azure Data Factory. On the project side, you determine how your data will be loaded. For instance, this configuration specifies data extraction from the source connection, landing it, and persisting it. It extracts data from the source system, saves them as Parquet files in a data lake, and retains them for future use. This data is then staged using a Databricks compute cluster. Within the Databricks settings, various configurations are available, such as Unity Catalog, Managed Tables, Global Parameters, and Temporary Views. These settings and potential overrides will be explored in subsequent sessions, especially concerning time zones. Once your project is set up, building it will generate all the necessary Databricks notebooks and Azure Data Factory pipelines. Let's examine the output post-build. Here we have the Azure Data Factory pipelines. All these Data Factory artifacts have been constructed and saved in our repository, in this instance, a GitHub repository for development. The copy activity is straightforward. We've optimized the Azure Data Factory pipelines. The initial step involves configuring a high watermark lookup to extract the most recent data. The separate activity handles the copy process. This checks if there's any data to extract, ensuring no unnecessary operations. The data is then extracted from the source system and stored in the data lake. Another condition checks if any data was extracted to avoid unnecessary Databricks cluster operations, optimizing costs. This project also supports Data Vault, which we'll discuss later. It manages the staging process for both source and persistent staging. If Data Vault is enabled, it will also execute the Data Vault notebooks. And finally, within your settings, you have the option to determine if you wish to archive the files you've extracted. So, to elaborate, we're transferring and storing the data into the data lake. The next consideration is whether to archive those files. This is where the persistent storage feature comes into play. Once the data is archived, the initially stored files in the staging area are removed. All these preferences can be toggled on or off in the settings. At this point, specifically for Azure Data Factory, we also enable these global parameters. This feature is particularly useful when you have different environments to configure. For instance, if you have a development environment or a production environment within Azure Data Factory, you can adjust this value accordingly. So, in your development Azure Data Factory, you can set it to your development configuration, and in your production Azure Data Factory, you can adjust it to your production settings. Let's explore where the Databricks notebooks are located. When I navigate to my workspace, you'll notice it takes a moment to load. Within my workspace, under the repositories section, all my files are organized in the repository. I'll navigate to the Databricks folder, where you can see all the artifacts related to Databricks that have been created. One of the primary components here is the table scripts. Inside the tables folder, we have scripts for various tables. Let's focus on the staging environment for now. In this directory, there are several Python scripts ready to be executed. Examining one of these Python scripts, its function is to deploy all the table DDL notebooks. I've already executed this, and there's a corresponding table DDL script for each notebook. This script is designed to accept parameters, determining which catalog or environment it should operate within. A lot of this process is customizable. Additionally, when considering the data loading into our source system based on specific requirements, there's a primary activity, a Python script. In the context of persistent staging, this script determines whether a full process or a delta process is required. For those unfamiliar, if it's your initial time loading data into Databricks, often you might be ingesting a significant amount of historical data. In such cases, a full load is preferred since there's no need for data comparisons. Subsequently, there are individual SQL scripts responsible for the actual data loading. As evident, there's an extensive use of native Databricks code. All these scripts and notebooks are stored in your GitHub repository, facilitating deployment through your continuous integration environment. In conclusion, this was a brief overview of the new Databricks automation within BimlFlex.